Hi, everyone, and welcome to the after show of the AI hardware show.
The after party.
The after party.
Yes.
This is our podcast format. It's a more relaxed conversation about the AI chips you've probably just watched about. If not, links to the episode in the description below. My name's Ian Cutress. I'm with More Than More, and joining me is Sally from E Times.
Hello, everyone.
This episode is a bit of a melange of chips, right? And I've got the list in front of me because some of these are so obscure, we still need to refer to notes.
Some of these are new. It's not really the same as obscure, but some of these we don't know as much about. Yeah.
That's the PR word.
Okay.
New, not obscure.
New.
So first up is Enflame Cloudblazer. Enflame.
Enflame.
We were having a debate about how it should be pronounced at the beginning of writing the scripts and the read through. Enflame.
I still think it's Enflame. Like it's going to catch fire, but I still don't think it's a great name for a chip. By the way.
Cloudblazer. Yeah.
Yeah. Okay. Enflame.
Any reference to fire is perhaps not so good.
Someone tell Blaze.
We'll get to them in a later episode.
We have another rant about their name.
But Chinese company, lots of hardware coming out of China. They showcased their architecture, Hot Chips 33. The first version, the DTU, because it's got to have a T in it for some reason. 1.0, 12 nanometer. They've got a DTU 2.0 coming out. That has come out, but there's not really many details about it. Machine learning, training and inference, and mostly focused on data center compute. It's another one of these big, aims to be big, high-end training chips that you connect loads of them together and you do your big models. Are we at a market saturation point now for these big chips?
Well, it depends how many competitors you think the market can support. Because I think you and I both know it's NVIDIA. It's all about NVIDIA. And if you're going to go up against NVIDIA, how many can go up against NVIDIA really like this?
Well,
so Enflame being in China, maybe they, have got Chinese customers that maybe we don't know, maybe we don't know. But I think, how many can the market support as well as NVIDIA?
Well, okay, so this is 12 nanometer. And 14, 16, whether it's TSMC, Samsung, or Global Foundries, the US really hasn't put a hammer on those 12 nanometer chips. So arguably you can make as many as you like, as long as you can optimize it. Because we're seeing other companies in on-flame space like Biren get hit by some of these limitations.
Yep.
And so you got to think, well, where's the scaling factor in these essentially GPU-like big training chips? To your point, I think China's the obvious market for this sort of stuff because everywhere else you're going to buy NVIDIA.
Basically, yes.
And
that's what we see right now, right?
Everybody keeps asking me, what's it going to take to dethrone NVIDIA?
A lot at this point.
Yeah.
2 years ago, maybe, but now, no.
It's for companies like OnFlame trying to do these big chips. The important thing, I think, is to get people hands-on. People understanding how to program for the network.
How to write code for this and how to,
Yeah, because NVIDIA's had that 10-year
absolutely
academic.
And the CUDA is so well respected.
Yeah.
And so everybody knows how to do CUDA and everybody does CUDA. And it's so, it's going to be very difficult to unseat CUDA, I think.
Yeah. Also, CUDA has so many more use cases, not just machine learning as well. Yeah, it's going to be tough. Companies like this, I think they're going to find like a key customer or two key customers, and they're going to go down that route, and it's going to be hard for them to get any more. And the customer likes it because they get a highly optimized version. And also with these Chinese companies, acquisition and IPO, which is usually the route out for these startups, is fairly limited because China. Yeah, I mean, the only people who can acquire you are Chinese companies.
Yes.
In that sense.
Yes, okay.
So.
That's a good point.
I mean, I don't know. I like the fact that, chips like this, they're supporting from FP32 all the way down to Int 8, and they actually came to a big event to talk about their architecture. Again, something that these companies need to do in order to get people on board.
Absolutely. They need to come and tell us about it.
Yeah.
We can tell everyone.
So all you chip companies out there who don't have architectures listed in your white papers,
come and tell us.
Come and tell us. Come and tell us.
You know who to talk to.
So yeah, Enflame, glad you came to talk. Talk more, please. Please. Salience.
You want to talk about Salience next? I mean, total 360 from from where we just were. Salience is a British startup. Obviously, we're both British, so we're like, does that mean we like them more or less? No, Salience. They're very early stage. They've just done a seed round, and it's out of kind of university research. But I think it's a really interesting idea. It's optical compute, which I know you. Yeah, he's like,
yeah.
Oh dear. So it is optical compute, but it's a slightly different idea to the other companies I think we've already spoken about.
Yeah.
More like a compute and memory scheme, I think, using basically shining light into it. I think it's going to be super cool. Whether it works or not, I think it's a fantastic idea. They have some proof points and so on in their original paper, and the guys, one of the founders has this PhD on it, and there's a great paper that you can go and read. But yeah, I don't know. I'm excited to see what they can do, but I think we're still quite a long way from product.
I can't remember whether I've done my optical compute rant.
I think maybe we've had at least one optical.
At least one. Well, okay. Recap for people who haven't seen those episodes. Normal optical compute is done with interferometers, right? Mm-hmm. It's the ability to make light in phase or out of phase. It's essentially a switch. What's a transistor? It's a switch. It's a 1-bit operation, right? In order to, and also interferometers are quite large to build in silicon.
Yep.
They require voltage control as well, so you need a slight digital element there. And then if you cascade enough together, you get some amount of compute. Okay, really fast because it's light, really low power because it's light, but it's not very dense. So you need to stack high. You need to build out wide. So optical compute, I think, right now, until we find another way to use light in that way, is best for transport and networking. However, as you say, these guys are doing it differently.
Yeah, just slightly different. And they retain some of the advantages, like you can shine in different colors of light and do 5 inferences at once or 8 inferences or whatever it is. Yeah. I think it sounds super cool anyway.
Well, that's the thing about compute that doesn't work when you're using interferometers. You can't shine different wavelengths of light because you either need the switch to be in phase or out of phase, not slightly in, slightly out.
Yeah, okay, I see.
Or at least if you don't usually use the amplitude of light as an input, because with interferometers, if you lose 10% every switch, you've only got like 6 switches before you've lost the signal completely. So the fact that this is trying to use the weights kind of like phase change memory.
Yeah.
Yes.
Shine light through it, and it's a bit less transparent or a bit more transparent. I think it sounds really cool.
But, when we see, I think a proof point is going to be, can we show it working on a ResNet 50? For as much as So I
want to see test chips. I want to see test chips, but it's still too early.
It's seed round.
It's very, very early, as we're saying. I think the other thing we wanted to pick up on from earlier was the tens of gigahertz. So you can run it super, super fast, but can you feed it that fast? I think we're a bit skeptical.
Well, so if you have multiple memory banks and you can do it in parallel, each one providing, say, memory bank running at 2 gigahertz. If you have 5 of those and the input can be modular. I mean, we go to conferences where there are papers about terahertz style electronics, whether that's wireless communications, and that's not limited in that way. We have optical fiber.
Yeah.
That's gigabit, hundreds of gigabits per second. And we're not relying on hundreds of gigahertz processors to feed it. So there is that. So I don't think that's that much of an issue, but does the frequency really matter when you're speaking about it? The frequency is determined by the wavelength, and it's your wavelength that you're more concerned about.
Fair enough. Yeah, fair enough. I think we'll wait to see what Salience comes up with.
Yeah.
When they come back with their test chips or so on.
the part of the problem with being a spin out from a university is that the people behind it have a very university-like mindset.
Okay.
So they also like to supply to other universities, and we've seen startups do that and fail because they don't get customers or they don't understand business.
Yeah.
And I think some of the most successful AI hardware companies we have right now are ones that identified we need salespeople. We need to be able to market this product. We need to be able to take it to people and present it. And it's those that are doing the best, even if they may not have the best product.
Yeah.
So there's a bit of that involved.
Yeah, I mean that goes for all startups,
They have time.
not just optical or
Yeah.
British startups, but
No.
yes,
Yeah,
it goes for everyone.
that's fair enough. So Moffett, not Moffat.
Moffat. We're still saying Moffat.
I think I'll say Moffat until either the company wins or loses.
Oh, they changed their name to Moffat, and then you call it Moffat.
Because it's Moffat who does the Doctor Who writing, right? Yes, UK Doctor Who, whatever.
Yes.
I don't necessarily watch it, but the guy who's written by Stephen Moffat, so Moffett.
Do we know what Moffat is named after? Is it a place?
I couldn't find anything.
Okay.
I think they're a Korean company.
Oh, right. Okay.
But they came onto the scene because they submitted results to MLPerf, which benchmarking for machine learning, and I attend the briefings because it's fun to hear what they have to say. Especially,
Absolutely.
it's fun to hear what David Cantor has to say.
Hello, David.
Hi, David. But we obviously get all the companies who have submitted obviously bring somebody in, and if there are questions from the press or analysts, because
you and me, yeah.
And the last one, was it the last one? I think it was 2.1, where new company has got a result, and like, who are they? What did they do?
Yeah.
So, yeah, there's a lot of questions there. I was like, you got an email? Are you going to tell us any more? And I think they've got a white paper on the website now. And yeah, Moffat. I'm already saying it wrong. Moffett's thing is to do with sparsity. Now, sparsity has been a kind of thing in machine learning since NVIDIA started inflating their numbers with it.
Yes.
Inflating. And
doubling.
Doubling. The idea is that when you have your matrix multiply accumulates, you're multiplying either a matrix with a matrix or a matrix with a vector, and that's obviously the compute intensive part. But if most of your items in your matrix or your vector are zeros or near zero, then you can prune or use a floor function, use a ceiling function. I think softmax is the operation where you try and pin some of those data points, and then if you end up with a bunch of zeros in at least one matrix, you have sparsity. And it's the clever engines that dictate you've got 0 multiplied by 0 plus 0. Therefore, anything multiplied by 0 is 0, regardless. And if you can recognize that before it happens, you don't need to do the operation, because if you tell a computer to multiply 0 by 0, it will still try and do it, and it will still try and consume power. Or you can have like a bypass lane and essentially save that power because the result is 0. And Moffett, I almost said Moffat again. Moffett's thing is, okay, GPUs, NVIDIA, they're dealing with single source sparsity. So in a matrix, one matrix is sparse. With dual sparsity, both matrices are sparse. So it's kind of like a 1D problem going to a 2D problem, but I'm pretty sure the complexity isn't linear.
Yeah.
It's probably quadratic or something else. So obviously, if you build a chip optimized to take advantage of sparsity, that's great. If you can take a chip to take advantage of 2 types of sparsity, even better. So Moffett in this case saying anywhere from 8x to 32x over competition, possibly 1000x in the future. But all the chips they've designed so far, I think it's the S4, the S10, the S30, smaller chips to bigger PCIe card chips, they're all for inference right now.
Yeah.
And inference already is taking advantage of sparsity, pruning, optimization, because that's the low power, lower compute version. I think sparsity in training is where sparsity really wins. So these guys need a training chip.
But it kind of it's much harder.
Yes,
It's much more dynamic.
Yeah,
It kind of emerges during the process, so it's hard to know
yeah,
where these zeros are going to be.
yeah. Well, that's why some companies are putting in additional like CPU compute to be able to do some of these detections, whether that's RISC-V cores or doing the compute, the memory, and the matrix acceleration all in the same thing, like Untether's trying to do, and then move the data around because that's obviously complex. And how do you encode that data? You make it more efficient in memory bandwidth, and how do you get more than 20% utilization and all those?
Yeah, it's tough. I think sparsity is something we will definitely keep an eye on. There's different forms of sparsity. It's still I feel like it's still, I mean, the basics of sparsity with the zeros, yes, but it's more complex than that, I think. And I think there's a long way to go in terms of, I think we're going to start to see more elaborate sparsity schemes and so on. I think we're not taking enough advantage of sparsity just yet, and it's going to be interesting to see who does what and how they do it.
I mean,
whether they call it sparsity, sparsification, sparsify, like they all sort of mean the same thing, but sort of
declutter.
don't. People use them in different ways.
Yeah.
So it's still not very mature.
I'm pretty sure some of these companies are going to hire a sparsity engineer.
Yeah.
Because if part of it is how much can you optimize in software in the code itself.
Yeah.
As well. So
yeah. So Brainchip are pretty famous. They've been around for a little while already. Brainchip doing spiking networks, kind of before it was cool. So you know what I mean?
Are these the guys who did Spinnaker, or is that something else?
That's something else.
Okay.
But Brainchip has been around for a little while, not as long as Spinnaker, which is going back a little further. But
show my age.
Yeah, me too. So Brainchip, asynchronous digital for spiking networks. So no, I feel like there's a bit of a misconception when we talk about neuromorphic here. That it's going to be analog because the brain is analog. But Brainchip and Intel Loihi and some others, it certainly is digital. It's not analog that we're talking about, unless it is in some cases, but not here. So asynchronous digital, because it's all about the timing of the spikes and when the spikes arrive. And if some spikes arrive at the same time, that means something, basically. So, it's Brainchip are already on 2nd gen of their architecture. So I think for the 2nd gen, they've increased the height of the spike. You can make 8-bit spikes now. They previously had 1, 2, or 4-bit spikes, and now they've got 8-bit spikes. And they've also added some hardware support for transformers, which is nothing to do with spiking, but it's still very cool.
I think because the brain feels like it's 1 bit, right? It's either a spike or it's not.
Yes, exactly.
It's not necessarily the intensity of the spike, because as a chemical pathway, the intensity of the spike decreases with distance, and therefore you got to re-up the spike in order to keep it going down the network. That I think spiking in analog is the connection people make.
Definitely, yes, yeah.
Neuromorphic is kind of like the extra, and to say digital spiking is almost feels like an oxymoron.
Right, yeah.
When I think about it that way, it feels like an oxymoron.
Well, think about it as asynchronous electronics. Just think about it as being about timing.
Right.
And it's about when the signals arrive.
So I have a problem with that as well.
Okay.
Because you can have synchronous digital.
Yes.
That keeps a log of the time.
Right.
As well as asynchronous digital. So imagine you got a series of spikes coming in, and the digital computer, which is digital, it all runs on roughly the same clock. It just keeps a table of when the spikes occurred, and then it puts them into a neural network, whether that's spiking. Essentially each synapse is a table that consists of when the last spike was and how intense it was. Because it's digital, that's where I think the 8-bit works. You probably couldn't do that in analog as well.
No.
Or at least as accurately, so you're not getting the fuzziness of analog in there. But I think part of it is a limitation of my own knowledge of what a neuron and a synapse looks like in a digital format, because we're so used to the analog format.
Yes, for sure.
When they say chips with millions of neurons, digital neurons, you're like, what?
It's also because some companies start talking about neurons and synapses, and some companies just talking about, Mac operations and so on, and some companies are somewhere in between. So it's when companies start to describe it as the neuron, that's when things get a little bit.
There's no IEEE standard.
Yeah,
for
no, for
neuromorphic.
which, oh god, yeah.
And then other people are doing it, still calling it neuromorphic, but doing it differently. And some people have put it in their company name, and it's nothing to do with it. Yeah.
Yeah. Even exploiting sparsity concepts can be seen as neuromorphic in some ways.
No,
so neuromorphic is a little bit of a difficult word.
Yeah.
But for me, neuromorphic means spiking.
Yeah. Okay. There are some people who say we do neuromorphic, but it's not spiking.
There are, but I wouldn't use neuromorphic to describe them.
But Brainchip, it's Akida.
That's right.
Second gen.
So yeah, I have an article coming out soon, which will be out by the time this goes live.
Yep.
That you can check out more on the second gen. But yeah, it looks super cool, basically. And so they use so one of the things about spiking, and stop me if we've been through this before. One of the things about spiking is it's really difficult to train spiking networks.
Yeah.
So Brainchip kind of cheats. It's not really a cheat if it works better, right? They just use an ordinary deep learning network, train it as you would in the normal way using backpropagation, but you can't really apply backpropagation to spiking networks unless you can, and some people do. But Brainchip kind of cheats. They convert from deep learning networks into the spiking domain.
Is that hard?
So they make it sound very easy.
Right.
Is the answer. But no, they do. So there are like spiking equivalents of convolution and so on that they use.
Yeah.
And hence you need the different you need the 8-bit spikes. You need the spikes to have a payload as well as just the timing.
And the spiking transformers.
Yeah, I don't know how the spiking transformer works. So I don't think it's the spiking transformer. I think they've added something else for transformers.
Right.
Which is separate, but
it
could be interesting.
So going from a startup that has chips to a company that may not create any more chips.
Yeah.
Huawei. So full disclosure, I wrote a lot about Huawei smartphones when they were big in the industry. I mean, I'm literally still wearing my Huawei watch. I'm pretty sure the Chinese government have all the information about me that they will ever get.
They're so interested in you.
Yeah. No, well, and I end up with a few excess devices, old sample units that ended up in the hands of friends and family. So
they think that's all you.
Yeah. Well, I don't know. Well, they've definitely got a personal profile. Whether that's Huawei themselves or the Chinese government, let's not get into that. But Huawei is under the US entity list, which means essentially US companies can't work with them to the point where they've even turned around to TSMC, who have partners and facilities in the US. They've said to TSMC, you can't sell chips to these companies either. So Huawei, it looks like right now, will never make another 7-nanometer chip at TSMC while this goes on. Now, their Ascend product line in machine learning, some of it was 12 nanometer, some of it was 7 nanometer, and it's the big boy 7 nanometer chip, obviously, that there will never be any more of again. And this is meant to be their big GPU-like training that is probably very widely deployed internally. Though again, not sure where the customers are, but Huawei drinks its own Kool-Aid, essentially. The 310, the smaller one, yes, that can be used for customers because that's still 12 nanometer. It's based on the DaVinci architecture, which is also in their smartphones, unlike Qualcomm, which we'll talk about in a future episode, where the architecture is completely different. Huawei decided to use the same architecture in its smartphones and in its chips that it no longer makes, and now the AI hardware that it no longer makes. But actually, as we're recording this, it's MWC week. And I've been seeing tweets. Huawei is usually a big player there, smartphones, whatever, but it used to be a third of their business was telecommunications. And we're in the UK, where Huawei equipment is now banned, I believe. And in the US, it's obviously been banned for a while. But they had a substantial amount of Hall 1, more than they've had in previous years, apparently.
Interesting.
So they're really driving hard on the communications business, which it looks like 5G comms doesn't necessarily need always the latest leading edge. because it's analog, and analog isn't always in leading edge process nodes.
Yeah.
Digital is a bit harder. But
yeah.
Yeah, so I'm not sure we'll ever see much about Huawei's AI hardware again because it requires that leading edge digital.
So they may, yeah, okay. What other alternatives to TSMC? I mean, can they make it somewhere else in a slightly lesser node, or what are they going to do? They want to continue to use it internally and continue to work on it.
I don't know the ins and outs whether the US has pressured Samsung yet. Obviously, Samsung 753 is good, but there are reasons why companies have been moving to TSMC for the leading edge. We have SMIC, SMIC, or UMC. They're the two big fabs in China. SMIC claims to have created 7-nanometer chips without EUV. Now, TSMC's first 7-nanometer generation wasn't with EUV either. It was DUV only. But that requires things like quad patterning and lots of different techniques that end up being very expensive to produce a 7-nanometer chip. If you can use EUV, it like cuts 4 steps down to 1 in lots of different areas of the process. So if SMIC are able to scale out that process, then Huawei have an expensive solution to go down that route.
Right.
And probably at a time when the rest of the world is on 3 or 2 nanometer or whatever. So,
yeah. I mean, so for data center, what are we refreshing every 4 years? Like they have a few minutes to figure it out, but not very many minutes, considering they need to probably be working on it.
I know it's still AI hardware, right? AI hardware. Anybody who isn't doing transformer networks now in training, is kind of left in the dust. We've seen companies that used to focus solely on convolutional neural networks are no longer getting the customer base they wanted because their architecture wasn't flexible enough.
Exactly.
So Huawei has HiSilicon, which is its like subdivision that purely does its silicon development. And I know after the entity list, they lost a lot of people.
Yep.
But still strong in infrastructure. So yeah. Huawei also has its ARM-based server chip. I'm trying to think of the name now. It's eluding me. Not UTN, but they're like one of the biggest creators of ARM server chips.
I didn't know
outside of Amazon.
Okay, that's interesting.
Because they made tons of them, deploy them on their own infrastructure.
Yes.
And then everybody else coming up behind is Ampere.
Yeah.
Computing has got the ARM chips. And then aside from that, there was a report out recently that ARM powers 5% of the server market. This is not an AI thing, by the way, but
no, but
just yeah. So there is that. There is pedigree there. Unfortunately, so many of the restrictions are just I don't know.
I mean, maybe the kind of regulatory environment will change. I don't think it's going to change. I personally don't believe it's going to change for the better.
No.
But we'll see.
I mean, politics is politics. I don't try to get involved, especially when it comes to chip production, chip design. I'd much rather it was all big one, quote unquote, happy family, where you have 1,000 companies making chips on 10 different foundries.
Yeah.
All with various pluses and minuses.
If you choose a particular foundry, it's because it's the best, or if it's for a reason that is related to the technology, not for artificial reasons like this.
Yeah. And a lot of those people are probably already in chip design houses elsewhere as well now.
Yeah.
Because if somebody says we can no longer use the latest process node, and you want career and advancement, you're going to go to a company that offers you that opportunity to develop your portfolio.
Absolutely, yeah.
So, and again, because I've been spending a lot of time on the training chips, and Sally's been spending a lot of time on the inference chips, we again flip from training to inference.
Back to inference. Well, back to the actual, edge or endpoint, like right back to the endpoint.
Back to the edge.
This is for like smart doorbells, smart home kind of items, consumer electronics. It's Kneron when we're going to next in Taiwan.
Kneron with a K.
Kneron with a K.
Kneron.
Well, it's got to be Kneron, hasn't it? Kneron have been around for ages, actually. relatively speaking. A lot of the companies we talked about here are very new, but Kneron have been around for years and years. I think 2018, they launched their first chip in 2019, so they have been around for a long time, but they started as a company that was making algorithms.
Right.
They were making facial recognition algorithms with
Software.
Very high accuracy. Yes, like writing the algorithms. And they have
computer vision, not machine learning.
No, machine learning.
Okay.
Like very early. So this is like, I don't know, 2015, 2016, 2017, 2018, that kind of time frame. So they have deployments already for those algorithms in like security kind of applications. But yeah, it's kind of an interesting aside. But yeah, so they started making IP then for the algorithms that they had, and then they decided to become a chip company as well. And that normally when companies offer both IP and chips, it's more on the IP, less on the chips. But this company has several different chips, different things. The first one was more towards kind of consumer electronics, the doorbells and so on that we're talking about. But
video doorbells?
Yeah.
Or just regular doorbells?
Video doorbells, smart doorbells, security systems, security cameras.
Anything with a video camera? Anything
with video, yeah.
Okay.
It was CNN optimized. Yeah. The second or the next kind of generation of parts really is they're going for automotive.
Lots of cameras in automotive.
There's tons of cameras in automotive, but it's really, really hard to get into automotive customers as a chip startup. It's kind of famously really, really tough.
As a chip startup and also as a non-Euro US.
Yeah, absolutely. Well, there are car companies in China also, but they
yes, okay, there are.
There are. It's very like, especially with some of these European ones, it's like if you start talking to them today, maybe in 10 years' time, they'll place an order. And if you're a startup, it's like you're dead, basically, in 2 years. So you need something else in the meantime, which I think is part of what Kneron is going for. We're seeing that with another kind of few chip companies, Blaze and a few others that said, you know, we're doing automotive, and then turns out, we're also doing smart home, smart retail, you know, all these other kinds of camera operations, which is absolutely fine. But just say that from the start, guys.
Well, so the automotive angle, say, okay, they get included in a solution, but it's going to take 10 years to market and the company essentially dies in that time.
Yeah.
It means that one of the other companies who's also involved in that solution, probably the SoC provider, can pick that company up and the IP for cents on the dollar.
And then,
roll it in and then it becomes their own.
Well, I'm not sure how complicated that was going to get from a design perspective, because you have to be quite far along from the design perspective by that time.
It's true.
You also have to have all your like automotive qualifications, your AEC-Q 100 and all that, which is not straightforward.
ASLD.
It's a lot for a startup to do. So that's why there aren't many startups going for automotive. It's a tough one. It's a tough nut to crack.
It's almost as if so the other side to automotive, we usually think self-driving is in-car entertainment.
Yeah.
So if you can do it for that, that's a bit more of a easier.
It's
again,
kind of a way in. So Kneron's way in is going to be aftermarket dash cams,
right,
and parking systems that you fit to your car, which have cameras, which you fit to your car after you've already bought the car. So it's kind of it's not really a loophole, but it's like an entry point for them into the automotive market.
The problem with aftermarket cameras on cars for parking is that usually battery operated, and one day that battery is going to run out.
And then you need to know how to do parking.
or you end up going straight through your wall, right? Yeah. So,
no. I wish them all the best with their automotive plans, but we know it's very, very difficult to do that. So, good luck.
If you've enjoyed this, then thank you. Please keep watching. More episodes are coming, either episodes of the main show.
More rants are coming.
Or more rants. There's definitely more rants coming. So, yeah, thank you, Sally.
Thanks, Ian.
Thanks, everyone, for watching.